Hello, my name is Grant McKenzie and I'm a teacher at Porthcawl Comprehensive School, and I'm working with Callum Cymru on AS statistics hypothesis testing. So the first sort of slide is the understanding of why we use hypothesis testing. I've sort of put an example here, and then I'm going to go through why we use it, what's the significance of it in terms of like the 10%, 5%, 2.5%, 1 and 2 tail tests, and setting out how it's expected to be written for sort of the perfect exam answer. And I'm also going to look at the binomial, making sure that you understand where they come from. Okay, because there's 3 forms, or there's 3 ways in which you can calculate the binomial. Either via a formula, then you've got the stats tables that is given to you in the exam, and then finally using your white calculator. Okay, I know they're a little bit sort of changed slightly the sort of the format of them, but I would highly recommend, there's plenty of videos out there for you to sort of look and understand how this calculator works. So let's get into an example. Understanding the use and why we use hypothesis testing. I've taken a particular example here, and then hopefully you can understand where I'm coming from. So Tom has psychic powers, or at least he states he does. He will guess what suit, so he's got a pack of cards, he'll guess from an audience member what suit has been pulled out from the pack of cards. So we say that the probability of getting the suit correct is a quarter, or 0.25. He will do this 20 times. Now what hypothesis testing will do, it will determine whether or not, if he gets it right over a certain number of times, does that mean it is luck, or does it mean statistically he has got psychic powers? You would expect, because it's 0.25, you would expect 5. He would get it at least 5 right, because the probability states the 0.25 times 20. But how many would it be before you're then thinking, statistically, he must have psychic powers to get all of these right? It doesn't automatically mean it's going to be 20. It just means that there's a critical region for it. So again, using x, so it's normally the random variable x we use. They can be for other different letters used depending on what it is. And then we're told that this is the binomial, because in AS maths, that is all we're using. When you go to A2, you will use other values, but the hypothesis testing is still the same. So it's imperative that you get it right and you understand exactly what the need of it is at this point. And then obviously you've got 20, which is the set number of trials, and 0.25, the success that he picks the correct suit for the card. If we were to look that px is greater than 12, it is approximately 1, okay, correct to 4 decimal places. So we can say that if Tom gets 13 of these correct, statistically he's a psychic, okay? And that's all we're basing this on. This is maths, so we're basing it on statistically. Some of you might say, well, is that true or not? Mathematically, if he gets 13 or more correct, statistically, then we would class him as a psychic. So how and what is our critical region? Well, if I go to the next page for this, I have said that for px greater than or equal to 10, and I will show you how you do these calculations, it would be 1 minus the probability x is less than or equal to 9, and that is equal to 1 minus 0.9861, which is 0.0138, and therefore is approximately 1.38%. Because let's be honest, that's what significance test is dealing with the percentage. So at the px greater than or equal to 9, we would do 1 minus px less than or equal to 8, which is 1 minus 0.99591. I'll show you how you do these calculations shortly, and that is 0.0409, which is approximately 4%. And then px greater than or equal to 8 is 1 minus px less than or equal to 7, which is 1 minus 0.8952, and that is equal to 0.1018, which is approximately 10%. So I can say with confidence, if Tom gets 8 cards correct, Yep. That would mean that 10% of these occasions he would have 8 or more correct answers. 10% is quite a high number, mathematically that is. Okay, and then 7 is going to be a lot more. And as I said before, a quarter of 20 is 5, so you would expect anybody to be just guessing would get 5 correct. On this occasion, if we say at the 5% significance test, so at the 5% significance test, if he got x greater than or equal to 9, you would say that would be our critical region at the 5%. X is greater than or equal to 9 at 5%. Okay, and then obviously at the 1%, because 10 was 1.38, still not smaller than it, so at the 1%, x is greater than or equal to 11. So if he got 11 correct or more, you would expect then at the 1% significance test that he was a psychic. And that's basically what we're doing, but instead of doing it for Tom being a psychic, pulling him up, we relate it and put it correct to any of the questions that's given to us. Okay, so what I'd like to go through for the I'd like to talk to you a little bit about how the binomial works. Okay, so this is the tables. There are going to be some questions which the tables won't do because the probability is 0.01, 0.02, all the way up to 0.02, and then it flips and keeps on going. Okay, so for the first example, I just want to show you and get into how this works. So if we say the random variable, this is just talking about the binomial, nothing to do with the hypothesis. The random variable, and then x belongs to a binomial, and this is going to be 7, 0.2. Find the answers to the to 3 sig figs. Find the answers to the following. To 3 significant figures. Now, as I said, calculator, using the sort of equations, it's going to be a little bit complicated, especially if there's a large, n is large. Using the tables is going to be good as long as the probability of success is going to be there. But using the white calculators where you do menu 7 and then it's binomial PD or binomial CD, that's the calculator that you're going to be using. I know they cost £20, but it is so useful to put them in, and they will be used in A2 Maths as well next year. Okay, so if you can get a hold of one, please do. I'm going to use the tables to show you how it works. So for px equal to 3, I don't like that, I need to rub that bit out. Equal to 3, that would be, because these are cumulative tables, the value at 3 is for 0, 1, 2, 3. So we'll do px less than or equal to 3 minus px less than or equal to 2. So in the tables, n is equal to 7, which is our set number of trials. The probability of success is 0.2. Remember that a success or failure probability is constant, set number of trials, and they're independent of each other. Those are the 4 sort of 4 things that you need to have if you're going to use the binomial. Okay, and sometimes they will ask you what assumptions you've made, and then you have to relate it to the question. I've got a couple of those, so I'm not going to sort of spend too much long on it. I just want to talk about the binomial. So if we have n equal to 7, 0.2 is here, and then we just pick up the values from here. I've highlighted this one at x is 2, just less than or equal to 2, just because it made it easier from when you're looking at them. So here we would have the values of 0.96676 minus 0.8520, and that is equal to 0.1147, which is approximately 0.115. And for the basis of us, these probabilities, we're going to convert into percentages. So that's 11.5%. For the next one, I want you to do, what is the probability of x is greater than 1, but less than or equal to 4. So how we would work this, px is less than or equal to 4 minus the probability that x is less than or equal to 1. And again, you just take the values from here or use the calculator and it would be shift menu 7. 9953 minus 0.5, and then that is 767, and that would give you a value of 0.4186, which is approximately 0.419, which is 41.9%. You're not really going to see that one. This is another one that you will see. Would be probability that x is greater than 1, and you would say that is 1 minus the probability that x is less than or equal to 1. Another way in which they can write this is the probability that x is greater than or equal to 2. It means exactly the same thing. You're still picking up 1 minus x is less than or equal to 1, and that would be 1 minus 0.5767, and that is 0.4233. Okay, so that's how you take it from the tables. If you look at all these values, they're all in this sort of section here, and then you can pick them off from the side. N equal to 7, which is the one I wanted from the tables, and the probability of success 0.2. Moving on. Okay, so here's my sort of step-by-step guide how I would answer a hypothesis testing question. Okay, so we have define x in the context of the question. It always has to be related to the context of the question, not just x is, I don't know, some beans. Okay, it needs to be specific to what they've asked you to sort of calculate and to find out. Then you've got H10, the null hypothesis. That's the probability is equal to a specific value. Then you've got H1, where you have P, the probability is greater than that value, or the probability is less than that value. We call these a one-tailed test. It's not equal to, it has to be specific and strict inequalities. As I said, this is a one-tailed test, so then your straight shootout, if it's 5%, you're looking to see if it is below 5% or above 5%. If it is sort of, that's your critical region, shall we say. So if it is below 5%, then you would reject H0. If it's above, you would accept H0 and continue that nothing has really changed. Then if it states that the probability does not equal, so it doesn't know if it's greater than, it doesn't know if it's less than, but they believe that there is a change in there. So how you would sort of state that would be P equals, and then a slash between the equals to show that it doesn't, so probability doesn't equal whatever the value is, and this would be classed as a two-tailed test. So again, you would sort of work out what the probability is, and if it's at 5%, you split the probability in half, because it could be greater than or it could be less than. So during that, you cut it in half. So if it's at say 3%, you'd cut it in half. So you're looking at, if it's less than 1.5%, you would reject H0. If it's above that, you would accept H0. I always put part 4 down. Is you're stating that x belongs to the binomial, you're putting your n and your p down. Just stating your parameters, that's more for you. It can sometimes lead to a mark in the question, but as I say, it gives you sort of specifically what you're going to be putting into the calculator, and it helps you out rather than all of this sort of question being quite busy. You're specifically honing in on that part 4. So x is belonging to the binomial, you know what your parameters are, and then you can put it in. Now, this is the part 5. You're working out, using the information, what the probability is. So you're either going to be using the tables, or you're going to go to calculator, and you're going to convert whatever that answer is. Once you've worked it out, you're going to convert it to a percentage, and then you compare it. If the percentage is less than the test significance, then there is evidence that percentage at that percentage to reject H0. Rather than saying strong evidence, I would say that there is evidence at that percentage. So if it's a 5% significance test, then I would say there is evidence at the 5% significance to reject H0, or the 1%, and that way you don't have to worry about using that term strong or weak. You can just put at that 5% significance. If it's bigger than, then you accept H0, and there's no real change to it whatsoever. And then the last part, which is again really important, you relate it to the conclusion. Sorry, you relate the conclusion to the context of the question. So you tell the examiner Has there been a change? So obviously, if you're accepting H0, there is no change, okay? But it's still relatable to the question. If it is sort of smaller within the critical region, you're rejecting H0 for this. So there has been a change, whether it's got less, bigger, so on and so forth. Okay, so that would be for me specifically how I would want it to be written out. And you're also making it easier for the examiner doing so as well. Okay, on to the next slide. So I've got about 4 or 5 questions here. I've tried to take them from different exam boards so that way then when you go back and you start sort of revising, you've still got the WJC questions to be looking at. How I would use the next sort of bit of this video would be, I'd probably watch the first one so you get a general idea of what's expected, and then I would pause the others, I'd try them yourself, and then obviously pause it, play it, and then work your way through it. But as I said, this definition or this step-by-step guide helps you to sort of explain to the examiner and set everything out. So most of these hypothesis testing are 7 markers. Sometimes they sort of break it up for you and then lead you sort of to write down all of this sort of important information. Other times they just let it carry out the hypothesis test, which is the end part. You've got to realize as well that when you're reading through this question, you're picking up, and it might be an idea to write down sort of those important parts. Because it takes a while to read a question from statistics. If you think about pure, you sort of see it, it's only 1 or 2 lines, and you know exactly once you've hit that keyword what you're going to be doing. You've accessed that part of your brain, and then you're ready to sort of write it all down. With statistics and mechanics, they take that a little bit longer, and you've only got that hour and 45 minutes. Okay, you got about 5 questions in each, and you've got to work your way through them as sort of efficiently as possible. Okay. So here we go. Martin grows cucumbers from seed. In the past, he has found that 70% of all seeds successfully germinate and grow into cucumber plants. He decides to try out a new brand of seed. The producer of this brand claims that these seeds are much more likely to be successful to germinate than other brands of seeds. Martin sows 20 of this new brand of seed and 18 successfully germinate. Carry out a hypothesis test at the 5% level of significance to investigate the producer's claim. So again, it's back to that sort of, is it been a fluke that 18 have done them, or statistically, is this got a better percentage of success? So again, if you remember what we put in the first part was, define what X is. So X is your random variable and is the number of seeds which germinate. That's your first part. Then let's define your null hypothesis. So your H0 is saying that the probability is equal to 0.7, because that's a bit of information you were told here. 70% of the seeds successfully germinate and grow into cucumber plants. So probability is 0.7. Your null hypothesis is stating, null hypothesis is 0.7. Your alternate hypothesis, H1, is stating, but actually the probability is greater or better than that. So it would be greater than 0.7. So I am going to write in a different color. So therefore, because it is this inequality, this is a one-tailed test, and it's at the 5% level. This is just for me in purple. You don't need to see that, but it gives me an idea of what I'm looking at when my percentage. So if it's less than 5%, I'm going to be rejecting H0. If it is greater than 5%, then the null hypothesis H0 is going to be accepted. So as we're writing it down, what was the next thing? Yeah, my random variable X belongs to a binomial, and there was 20 of them trialed. So that's N, and that was at probability of success 0.7. And then we have said that Martin sows 18. So the probability of X being greater than or equal to 18. And again, you're either going to use tables for that. A table for 20 and 0.7 is very much in there, or you're going to be using your calculator. So the tables and the calculator, you're looking for the cumulative button. Okay. How you would do it on the white calculators is menu 7, and then you have to sort of drop down because the first 4 or 5, and then it would be 1 for binomial CD, and then you don't want the you want it to be variables. You would put in x, which is going to be 17. You'll see why in a second. The n is equal to 20, and the probability p of success is 0.7. So px is greater than or equal to 18 is the same as 1 minus px less than or equal to 17, which would give me 1 minus 0.965, which is 0.035. So we now have our probability, which is 3.5%, and that is less than 5%, our one-tail test. So what do we do? Well, we reject H0, because it is smaller than null hypothesis. Reject H0 as there is evidence to suggest at 5% significance test that the new seeds are more likely to germinate. Likely to germinate. Okay, so if you look back at the previous slide, we have defined what x is, the random variable. We have said H0, the null hypothesis, the probability, taking all this information from the question. We have then said that it's a one-tail test because you want to carry out the hypothesis to see whether or not the producer's claim is that they germinate better. So probability is greater than 0.7. We have then stated that x, the random variable, belongs to a binomial, and we put the parameters in, n and p. And then we have worked out the probability that x is greater than or equal to 18, because they've had 18 successful plants germinate out of 20. We've put this into the calculator read from the tables. We've got a probability of 0.035, which is 3.5%. That is less than 5%. So at this 5% significance test, we reject H0. So we've written a conclusion, and then we've said that that means the new seeds are more likely to germinate. So we put a conclusion in there as well. Okay, so if we go to the next slide, and the part 1 is what I've tried to do is looking at and helping you with the binomial. So part 1, where it is, again, if we read it, the probability that Janice sees a kingfisher on any particular day is 0.3. She notes the number x of days in a week on which she sees a kingfisher. State one necessary condition for x to have a binomial distribution. So again, if you think about, there are 4 conditions for it to have binomial. It's not acceptable to say, well, it's independent. It's not acceptable to say the probability of success is 0.3. It's either success or fail, or what was the last one? It's got a set number of trials. Those are not going to get you that 1 mark. What will get you a mark is if you relate them to that question. So you're either going to say that, so for part 1, either you would say that probability of seeing a kingfisher is the same each day, therefore independent. So probability of seeing, we've got enough room for this, a kingfisher is the same each day. So that is your saying about independency. Or you can say seeing a kingfisher on one day is independent of other days. So the first one, obviously, the probability of being successful is the same. And then the next one is seeing a kingfisher on one day is independent of other days. Kingfisher on one day is independent of others. of other days. So one of those, you don't need both of them. Part 2, assume now that x is a binomial distribution. So again, I would like x belongs to a binomial distribution, and it says she notes the number of days in a week. So it's going to be 7 days in a week, and the probability of success is going to be 0.3. And she wants to find the probability in a week Janice sees kingfisher on exactly 2 days. And again, you can either use the formula, or I'm just going to use the tables. And I've looked these up previously. So x is equal to 2 is the probability that x is less than or equal to 3 minus the probability, not 3. Let's change that, not 3, sorry, to 2 minus the probability that x is less than or equal to 1. Those then would be 0.6471 minus 0.3294, which would give me 0.318 to 3 sig figs. And then part 3 would be each week Janice notes the number of days in which she sees a kingfisher. Find the probability that Janice sees a kingfisher on exactly 2 days in a week during at least 4 of the 6 randomly chosen weeks. So now a binomial has changed, and this is why you need sort of the calculator, because if the probability of 0.318, because that's what we worked out in the second part, which is the probability she sees kingfisher on exactly 2 days out of the 7. So then again, so we're using this probability. That's not going to be in the tables. And if it is a large number and you're going to have to calculate it, you're not going to be able to, because there's going to be too many sort of computations to do it. So the white calculator would give you this information. You would just put it in as P. So here we have now got x belongs to a binomial, and there are 6, and the probability of success is 0.318. And it's asking you, what is the probability that x is greater than or equal to 4? Which is the probability, well, 1 minus the probability of x less than or equal to 3. So in this, x is less than or equal to 3, it is 0, 1, 2, and 3, which is 1 minus, and again, I worked this out previously, I just lost it. I just worked out the actual value itself. So if I delete that, put that in, and that was equal to 0.0854. And as I said to you before, what you can do is you can then look at these and work your way through them yourself. So number 2, it says it is known that 20% of plants of a certain type suffer from a fungal disease. When grown under normal conditions, some plants of this type are grown using a new method. Sorry, full stop there. When grown under normal conditions. Some plants of this type are grown using a new method. A random sample of 250 of these plants is chosen, and it's found that 36 suffer from the disease. Test at the 2% significance level whether there is evidence that the new method reduces the proportion of plants which suffer from this disease. So again, going back to what we've done in that 2 slides ago, state what x is, the random variable. So x is the number of diseased plants. So I'm going to put a line down here now so that we can know that this is question 1 and that this is question 2. You put in your null hypothesis. So this is the probability that x is equal to 0.2, that 20% of them. Your H1 is the probability is that it is less than 0.2, so that there are sort of less diseased plants by normal. Then you state your binomial. So x belongs to the binomial, and this time there are 250 of these plants, so that's n. And again, 0.2 is the success of them being sort of diseased. Again, using the calculator, because I don't think the tables go up to that far, it's going to be px less than or equal to 36. And we don't need to do 1 minus, because we're looking for, there are 36 of these which suffer from them. and that is equal to 0.0139 or 1.39%. Left it as 1.4, it's fine. So we're testing at the 2% significance. That looks too much like an 839 there. So I'm saying that 1.39 is less than 2%. Therefore, we reject the null hypothesis H0. So there is evidence to suggest, and I want this conclusion, evidence to suggest at the 2% significance test, at the 2% big test, only because I haven't got enough room, I'd expect you to write it in full, that the new method reduces proportion of diseased plants. Of diseased plants. Okay, I have got a couple more of these to do, but I am going to speed up so that I can fit them all in. Okay, next one. So we've got 3 left that I'd like to go through. And as I said, I've chosen each of these examples because they give you something slightly different. So it is known that under a standard treatment for a certain disease, 9.7% of patients with the disease experience side effects within a year. In a trial of a new treatment, a random sample of 450 patients with this disease was selected. The number X who experienced side effects within 1 year. They have sort of stated their X now. Okay, so they've stated the random variable X. They experience side effects within 1 year, so you don't have to. State an assumption needed in order to use a binomial model for X. Again, if I put the assumption over this side, your assumption is basically independence or probability is constant, but it needs to be related back to the question. So you're either saying the patients are independent of each other, so they're not from the same family or anything like that. Patients are independent of each other. Or you're going to say that the probability of side effects is the same for each patient. The probability of side effects is the same for each patient. And that's your 1 marker there. Then we've already, as I said, stated what X is, experience side effects within a year. So it was found that 51 of the 450 patients experienced side effects within 1 year. Test at the 10% significance level whether the proportion of patients experience side effects within 1 year is greater under the new treatment than under the standard treatment. Okay, so as we've done X already, we can just go straight into a null hypothesis. The probability is equal to 0.097. Up here we were told about the 9.7%. We need to convert it into a decimal. Our H1 is stating that test whether or not proportion of patients experiencing side effects in 1 year is greater, so then we would put greater than 0.097. X belongs to a binomial, and it is 450 patients, so that's my N, and then 0.097 is the probability. We're saying that the probability that X is greater than or equal to 51 is equal to 1 minus the probability that X is less than or equal to 50. And then that would be 1 minus 0.862, which is 0.138. So 13.8% that is greater than our 10%, because remember this is a one-tail test, and they've asked at the 10% significance level. Therefore, insufficient evidence at the 10% level of significance. Level of significance, which means do not reject H0. Reject H0. There is no evidence to no evidence to suggest the proportion experiencing side effects in 1 year is greater than the standard treatment. Suggest that proportion experiencing side effects in 1 year is greater than the standard treatment. Experience in 1 year is greater than standard treatment. And again, related to the question. I put down here. Full stop. Okay, and now I like this question because it was almost like spot the mistake. Okay, they've already stated out what is exactly required. They've done the hypothesis, and then you've got to then come along and see, so sort of test your knowledge that little bit more. Okay, so past records show that 15% of customers are shopped by chocolate. Shopkeeper believes that moving the chocolate closer to the till will increase the proportion of customers buying chocolate. After moving the chocolate closer to the till, a random sample of 30 customers is taken, and 8 of them are found to have bought chocolate. Julie carries out a hypothesis test at the 5% level of significance to test the shopkeeper's belief. Okay, and she has then obviously gone through PX H0, the null hypothesis, is equal to 0.5. H1P is greater than or equal to 0.15, sorry, 0.15 above. X is the number of customers who bought chocolate. Binomial, 30, 0.15. X is equal to 8. And then obviously rejecting H0, so there's sufficient evidence. Identify 2 errors that Julie has made while doing this. So the first one is that so if I put A up here, H1 needs to be P is greater than 0.15. It's a one-tail test, so it is greater than, can't be equal to. If it's equal to, or not equal to in this case, then that would be a two-tail test. Can't be equal to, because otherwise you've got the H0, you're not really testing anything. And the other thing is this part here, so it's this one and here, where you are saying that the probability of X is greater than or equal to 8, and that's what you're going to be testing. Explain whether or not these errors will affect the conclusion. The second one is going to affect the conclusion. So you would need to Px greater than or equal to 8 is equal to 1 minus Px less than or equal to 7. And that is going to be 1 minus 0.9302, which is 0.0698. Therefore, 6.98%. which is greater than 5%, so we do not reject H0. Put that on around. Do not reject H0. And then find, using the 5% level of significance, the critical region for the one-tail test of the shopkeepers. So then at the 5%, so we know it's not 8, it's going to be quite close. So let's try for part C, Px greater than or equal to 9, 1 minus Px less than or equal to 8. 1 minus 0.9722, which is equal to 0.0278. So this is 2.78%, which is less than 5%. So that's my critical region. So my critical region is x is greater than or equal to 9. And then part D, find the actual level significance of this test. Well, it is going to be 0.0278. I thought it was a really nice question. Okay, and then my last question. So the last question is sort of leading you into it, okay? There's lots of little parts where it's then sort of making you work through the hypothesis. A nursery has a sack containing a large number of coloured beads, of which 14% are coloured red. Aaliyah takes a random sample of 18 beads from the sack to make a bracelet. State a suitable binomial distribution to model the number of red beads in Aaliyah's bracelet. So we're going to put R, it could be X, it doesn't matter. R is the number of red beads. Of red beads in the bracelet. We're also going to state, I like stating R is a binomial and it is 18 0.14. It's just taken from the questions. Part A. Part B1. Using the binomial distribution, find the probability has exactly one red. So P R is equal to 1. You should sort of just write it. X. And that is going to be either read off the tables or 194 or on your calculator. For part 2, there are at least 4 red beads. So we're saying that Px is greater than or equal to 4. You're used to this now. So it's 1 minus that Px is less than or equal to 3, which is 1 minus 0.7618. And to 3 sig figs, it is 0.238. C, comment on the reliability of the binomial distribution to model the situation. I would say it's only going to be reliable if the probability of getting a red bead stays the same at 0.14. Only going to be reliable if the probability is constant of getting a red bead. At 0.14. And then after several children have used beads from the sack, the nursery teacher decides to test whether or not the proportion of red beads in the sack has changed. She takes a random sample of 75 beads and finds 4 red ones. Stating your hypothesis clearly, use 5% significance level to carry out a suitable test for the teacher. So again, we stated R, so I can move on with that, and it's sort of obviously 4 marks. So H0 is P equals 0.14. Now H1, our alternative, is actually, we don't know if there's a change. We don't know if it's a positive change or a negative change. So we're looking to see what that change is. So we would then write X belongs, not X, R belongs to a binomial, and it is 75 0.14, where the probability of X is less than or equal to 4 equals 0.01506. Now, this is 1.5% approximately, and this is less than, and now because it is a two-tailed test, our percentage is 2.5% significance, because you have to divide the 5% significance they asked you for by 2, because you're looking for the upper part and the lower part. So this is actually 1.5% is less than 2.5%. So reject H0. So there's sufficient N at 2.5% that the proportion of red beads has changed. Proportion of red beads has changed. I hope that has been helpful, and this is the last one for this year. So I hope you're looking through the videos, and if you go on the website, there'll be various other videos that you can look forward to seeing. Thank you very much.